As we know that S, P, D, and F subshells are at different energy levels, at different energy levels. When they intermix, they intermix, they produce degenerate hybrid orbitals, hybrid orbitals, which have same energies or affinity toward making the bonds over there. Same energies are affinity for making bonds over there. Let's see what I should say over there. That, for example, I am saying when we observe the carbon structure over there, for example, 6 and 12, I am saying the carbon is there. And carbon is having 6 electrons, which according to electronic configuration, I will say it is going with 1s2, 2s2, 2p, also 2. Because S can maximum have 2 electrons, school, public school, like S, PS, DPS, like that. Will be used according to its arrangement. And here we know that S orbital is having only the spherical shape. S orbital is having a spherical shape over there, while the P subshell is having dumbbell shape and having 3 axis values over there in 3D shape as PX, as Py, as Pz over there. Then what will happen basically according to Hund's rule and Aufbau principle over there, I will say that 1s2 is not going to participate in any type of bonding purpose over there. But these 4 electrons which are present in P and S are going to participate over there. Then what will happen? 6 and 12 is present over there. Then we can say 1s2 is remaining as it is. But this 2s is going to lose its 1 electron for p orbital, and 2p is being taken as 2px, 2py, and 2pz over there. And this 2p, which is already having 2 electrons, also being shifting towards py, and s is shifting towards 2pz over there. Now every shell which is in the form of, because 2px contain maximum 2 electrons, and maximum 2 electrons, but it does not happen in reality. Then what will happen over there when this complete block of 1s and 3p, because P we know at the higher energy level is going to intermix with the inner shell of S subshell, which is lower energy level, in which I am saying 1s and 3p are going to intermix. Then I am getting sp3 hybridization, in which I will say if 1s and 3p subshells intermix to form or to generate, to form hybrid orbitals, of same energy level, of same energy level, some energy level over there, then we can say it should be taken as sp31, sp32, sp33, and sp3, as four orbitals should be formed over there. And if I am taking here that one as how they are going to be produced, these orbitals, and how they are going to show their behavior. For example, I am saying here that I am taking alkane over there, alkane or ethane over there for the example, to show how this sp3 is going to happen, that the carbon and another carbon, because we can originally have the formula CH3 with CH3 over there, as you have studied in your organic chemistry of IGCSE over there. And when sp3 orbitals are present over there, they are going towards head-to-head overlap, as we have studied in the previous lesson, that when the head-to-head overlap is going to happen, then single covalent bond is formed, which is called sigma bond over there. One sp3 is going to being intermixed between one carbon atom to another carbon atom, another sp3, another sp3, another sp3 is also available, sp3, sp3, sp3 is available, and they are going to make their angle for hydrogen, for hydrogen over here, for hydrogen over here, because hydrogen is only 1s1. Hydrogen is only 1 is 1s1 over there. So S is in the form of spherical shape. So I tried to draw the circles for hydrogen over there. So hydrogen is present over there, hydrogen is present over here also, and hydrogen is present here over also. And according to the bond angle and the characteristics, then we can say the bond angle for sp3 hybridization is, bond angle will be taken as 109.5 degree, and the geometry of the molecule will be tetrahedral. After that, if I say according to the carbon structure over there, I say that 1s and 2p are going to mix up, but 2pz is remaining as it is. Then what will happen over there? For example, I say that the carbon with 612 is having its electronic configuration 1s2, 2s1, 2px as 1 electron, 2py as 1 electron, and 2pz as 1 electron. What I am saying here, that 1s is intermixing with the 2p's over there to produce 3 hybrid orbitals of sp2, sp2, and sp2 over there, but 2pz is not participating. Then such type of hybridization is called sp2 hybridization over there. And in this section, I will say when 1s and 2p are intermixing to produce 3 sp2 hybrid orbitals, over there, then we say that sp2 hybridization is going to happen over there. And in this case, where I said that 3 orbitals are present to produce their bonds over there, then what is happening? I am taking 2 carbons again, because we know that ethene will be going to form over there with making the parallel overlap of its bonds over there. Let's suppose I say it is my PZ, which has not participated in intermixing. Remaining 3 orbitals, one is sp3 orbital is present in along this direction, one is present along this direction. one is present to make the bond with another carbon atom in the form of a single covalent bond over there. And here I am again having an orbital and again having an orbital. Here I say they are going to mix up with hydrogen, mix up with hydrogen, mix up with hydrogen, mix up with hydrogen. But, and all of these are sigma bonds over there. And sigma bonds are formed because of head to head, head overlap. But for this PZ, the parallel overlap is going to happen. And this parallel overlap is responsible for the formation of pi bond over there, which will give its structure in the form of C double bond C with H and H over there, H and H over there. So I can say here sp2 is showing its behavior by single covalent bond present between carbon to carbon, hydrogen, hydrogen, and one pi bond is being taken into account. And here the bond angle will be the bond angle for sp2 will be 120 degree, and the shape of molecule will be trigonal planar over there. And in the last, I am taking again the example of carbon over there, in which I am saying, let's suppose the carbon is there 6 and 12 over there, and carbon is having again the same configuration according to 1s2, 2s1, 2px1, 2py1, 2pz as 1 electron to be carried. But right now, what is happening for sp hybridization, 1s and 1p are going to intermix to produce two hybrid orbitals of sp and sp hybridization over there. And 2py and 2pz are not going to participate in hybridization process over there. Then what will happen over there? For example, I am taking this carbon and this carbon. It is making only two sp orbitals over there. So one sp orbital from this carbon, one sp orbital from this carbon is coming to make sigma bond over there by head-to-head overlap over there. And one hydrogen atom is going to attach also over here. I am taking hydrogen not on this side. Just a second. I am taking my hydrogen on the other side. I'm taking hydrogen on this side. This is my hydrogen to attach. This is showing sp orbital to react with hydrogen as a spherical orbital is going to make its bond over there. And this carbon is again showing the sp orbital in the form of for hydrogen over there. And py is present over here. Pz is present over here. Here again, py is present and pz is also present over there. Now, what is happening basically? We can say these p orbitals are going to show the parallel overlap. This is also going to show the parallel overlap, which is responsible for the making of pi bonds over there. And these pi bonds are responsible for making a triple covalent bond between carbon atoms to make the ethyne structure over there. For example, I'm writing it here with the C. Sigma bond is coming because of the sp hybridization. Then double covalent, double bond, this bond is coming because of py overlap, parallel overlap, and pz parallel overlap is going to make triple covalent bond for carbon over there. And we can say here that only one orbital is present in the form of hydrogen to make over there. and a single covalent bond from this carbon on its ends, and single carbon hydrogen covalent bond is present to make the structure of ethyne over there. And this is the example of sp hybridization over there. Hybridization over there. So in case of sp hybridization, I will say that the bond angle is 180 degree, and the shape of the molecule is linear over there. If we just revise what is he saying in our lecture notes over there, he is saying a process in which different energy levels and shapes merge together to develop a set of orbitals of same energy and shape. Number of degenerate orbitals are going to form over there. Then we can say he is saying that this process is called hybridization, where he is saying they are intermixing and producing the hybrid orbitals, and hybridization is going to happen over there. After that, he is saying orbital hybridization is used to explain bonding and geometry, as I have explained about sigma bond, pi bond, and I have told about the geometry like tetrahedral and trigonal planar over there. And I have also tried to explain about the bond angles over there. So everything will be explained with the help of how they have expanded, and they are going to produce over there the sp3 hybridization sigma bond and pi bonds over there. As per VSEPR theory, valency is defined as the number of unpaired electrons in the valence shell of an atom, but this rule is not to be applied for beryllium, boron, and carbon. In the second period, all right, hybridization is happening. So he is saying sp3 hybridization, as I have explained, 1s and 3p orbitals hybridize to generate 4 sp3 hybrid orbitals over there, which are having the same energy and shape over there. When they have same shape and energy by making the 4 orbitals over there, then we can say, for example, as I have taken the example of carbon over here, now he is saying like 2px and 2py with 1 electron, and 2s is shifting his electron towards 2pz over there, and they are producing 4 sp3 orbitals over there. And when he has taken this, then the shape of tetrahedral geometry for methane he has taken over there is being taken into account by making the bond angle of 109.5. After that, sp2 hybridization, where he said that hybridization in which 1s and 2p orbitals are going to intermix to produce 3 sp2 hybrid orbitals over there. So we can say 2s is again going to shift its electron towards z. He has taken 2py, no problem. You can also take 2pz over there, which is responsible for parallel overlap, and sigma bond is being produced, sigma bond is being produced, sigma bond, sigma bond, sigma bond. But the parallel overlap is responsible for the we can say double bond over there. And he said the lower one is sigma, upper one is pi bond, and the bond angle is 120 degree, and its geometry is trigonal planar according to VSEPR theory. We have also explained about that. Then there is sp hybridization, which is given here, which means where carbon forms a triple covalent bond, and one single covalent bond is present. First bond from the double or triple covalent bond will be sigma, and remaining two others will be pi bonds will be over there. So till here we have discussed about sp3 hybridization, sp2 hybridization, and sp hybridization according to our basic concept over there. Now he is going towards ionic character in covalent substances. So non-polar molecules, they are in nature, and non-polar means they have only carbon and carbon like hydrocarbons. They have no electronegativity difference, no electronegativity difference. Then we can say they are non-polar. They are going to dissolve only into the non-polar solvents over there. And polar covalent molecules are those which are having oxygen in their structure, which are having nitrogen in the structure, like oxygen is added for carbohydrate molecules like that, or carboxylic acid, or alcohols over there, and nitrogen can be added into them like in the form of amino acids, or we can say simple cyanide groups over there are available to produce the compound as organic compound over there. Then these categories are designed on the basis of types of atoms or elements present in the electronegativity difference and geometrical shape of the molecule. Is it possible that he is going to show the behavior of polar and non-polar structures? And he has also explained about electronegativity, which I can say there that electronegativity is electronegativity. We have also discussed in chapter 1 with this. Electronegativity is the tendency of an atom, the tendency of an atom to attract the shared pair of electrons towards more electronegative atom, which I will say here towards more electronegative atom over there. Electron towards more electronegative atom. This is called electronegativity. And I told you that fluorine is the element which is having the maximum value of electronegativity, for which Pauling has given the scale. Pauling has given the scale. And the difference of electronegativity, if it is less than 1.7, then it is 1.7, then it is polar covalent. And if it is greater than 1.7, then I say it is going towards ionic compounds over there. And for example, I say here that the cesium fluoride is the compound which is having 92% ionic character, the most strongest ionic compound in nature over there. 92% ionic character is being carried by this compound over there. After that, non-polar molecules, he is telling now, non-polar molecules are those which are having zero electronegativity difference. For example, BeCl2, CH4, ethane, carbon dioxide, CCl4. Every scale is going to be cancelled out, and those are called non-polar covalent molecules because their electronegativity difference is zero. In case of polar covalent compounds, we say that, for example, HCl is present, CH3Cl, like methyl chloride is being taken, then only one chlorine is producing negative and carbon is behaving as carbocation ion, then it is going to show the polar characters of covalent compounds over there. So we can say here asymmetrical molecules with one lone pair is going to be responsible for making the electronegativity difference over there. Electrons in the central atom and in the molecule makes it polar. For example, AlCl3 non-polar and PCl3 is polar. Reason is only behind that it is having the lone pair over there. How I can go for its structure to be taken into account, like Al is a metal which is belonging from the third group. So it is having only 3 electrons which are participating and making this compound AlCl3. While when I go towards phosphorus trichloride, Cl, but phosphorus belongs from the fifth group over there. It is having a lone pair over there. And this lone pair is responsible for attracting the shared pair of electrons more strongly towards its nucleus. which is responsible for its complete showing the partial positive and partial negative ions to the solution of polar covalent molecules which are soluble in water, which are showing that they are having the characters similar to ionic compounds over there. After that, covalent characteristics in ionic compounds. An ionic compound is formed due to complete transfer of electron, a metal atom to a non-metal atom. We know about that. As like example, Na, a plus Cl2 plus 2Na. Then we say what is happening? Sodium is losing its electron in the form of plus 1e. And then also the chlorine is getting that electron. And then I can say here that it is going to produce Na plus Cl negative ion over there. And electrostatic forces of attraction are responsible for this compound formation over there with 2NaCl. This is the ionic bond over characteristics over there. Hence, we can say here the ability to attract the electron of the negative ion. Hence, distortion occur known as polarization. That is also being called polarizability factor is also involved. As a result, electrons come to the positive ions and negative ion developing the covalent characteristics over there. So there is much possibility that in ionic compounds, the characteristic of polarization is going to happen over there. So polarization power or polarizability of the cation, smaller cations with higher charge density have high polarization power to attract the electrons of the negative ion. Al plus 3 is because 3 electrons is lost, and that is the smallest ion, have high polarization power as compared to magnesium and sodium because they have only plus 2 or plus 1 charge over there. So polarizability of anion is going to be taken now. How anion is going to disturb the structure of a molecule. So larger anions with high negative charge are easily distorted. Is distortion like iodine with -1 because iodine is just above the astatine. Fluorine, chlorine, bromine, then iodine means its negative charge is very much far away. So high polarizability than bromine, then chlorine, like that. Chlorine is having very less polarizability towards the molecules. Comment on the amphoteric behavior of Al2O3 or explain AlCl3 water insoluble. The reason behind it that they can show the both characteristics of amphoteric, we can say it can behave as acid, it can behave as base, and acid and base according to Lowry-Bronsted concept, which can donate the proton, which can accept the proton is base and leave the proton is acid. Then amphoteric compounds are showing Al2O3 as a balanced phenomenon over there. AlCl3 because it is not having any lone pair over there. So it is going to show insolubility in water over there. So for today, we will keep it till here. And you will try to revise all of these topics over there, which were from the previous one. I am sharing this book with you and try to do practice of the previous topic questions also, which was before the VSEPR theory was present over there, like this one chapter.
Okay.
Related to ionization energy and a little bit which we have studied about the atomic size, how fast ionization energy of phosphorus is greater than that of sulfur, like that. I'm sharing at the end of the next chapter. You will also go for the practice questions over there. And tomorrow for the next class, like you have some question, we can discuss them over there.
Okay.
Okay. Thank you so much for today and see you tomorrow. See you on Saturday, inshallah.
Okay.
Allah Hafiz.
Thank you, Rufus.